Professor. Thank you very much.
Okay, thank you. Okay, thank you for the kind introduction, and my thanks to the RF and Microwave Technology Network for the kind invitation to be with you today. Hello. My role within BT is to look at the end-to-end 5G network architecture. So that's really the presentation I'll be giving today. What I'd like to do is touch on a lot of the kind of network aspects. We've heard a lot today about services, products, some of the capabilities we could see in 5G networks. But actually, what does that mean for the network? So let's start with a quick review of the IMT 2020 requirements, the official specifications from the ITU that we have to address with 5G technology. And then let's explore the 5G architecture as standardized within 3GPP. Now, I say as standardized, of course, some of this work is still ongoing. By June of this year, we should have a fully standardized 5G architecture with the next generation core, assuming next generation core is concluded within release 15. We'll talk a little bit then about the functional decomposition of the RAN. We've heard about CRAN today, but CRAN means many different things to many people, from cloud RAN to coordinated RAN, to cooperative RAN, and actually the functional decomposition of that RAN will determine the level of coordination and capability we can deliver. So let's explore that a little, and then let's kind of develop that into a 5G network architecture end to end. And then we'll look at how we optimize that architecture for products and services, in particular for low latency services. I'd then like to highlight a little bit of the work we're doing within BT and EE on our trials programs, and then just summarize briefly. I will talk about a 5G network architecture, but it's probably worth providing a little bit of context first. We're intending to launch with what's known as an option 3X network. So that will be a network which is effectively based on an evolved packet core, an EPC+. I talked in last year's presentation here, which is available on IET TV, about the various architecture options. So 3X is our short-term target. We'll then evolve that network to a 7X network. So it'll look like the architecture I described today, but it will involve release 15 LTE into working with the next generation core network. And of course, the full 5G architecture on option 2 network is effectively simply an option 7X after refarming of spectrum from ELTE to new radio. So that 7X network is kind of where we'll be for quite some time. And I say you can find an overview of this in my presentation from last year. So we've seen this particular slide a few times today, but it's worth just spending a few moments on it because we are trying to address a very broad range of capabilities, from enhanced mobile broadband to ultra reliable and low latency communication and massive machine type communication. Now, most of our focus to date is on enhanced mobile broadband. That'll be the go-to-market proposition. We're working a lot with verticals and with our colleagues in research on ultra-reliable and low-latency communication. And we're also working on machine-type communication, the Internet of Things. But primarily, a lot of that is being addressed today through the evolution of 4G, with the introduction of narrowband IoT and eMTC technologies. The MMTC aspect, the massive machine-type communication aspect, will be standardized in release 16 and evolve as a second phase, effectively, of 5G. Now, interestingly, in terms of data rates, at the top it talks about gigabytes in a second. So gigabytes, plural, 8 bits in a byte. So in excess of 16 gigabits per second, and we'll see what that means for the ITU spec in a moment. Lots of heavy data applications around 3D video, ultra-high definition, augmented reality, virtual reality, and we've just heard a lot about some of those examples. So these kind of services will drive huge data rates onto networks and huge levels of concurrency on networks as well. So in terms of a few selected parameters from the spec from the ITU, initially we're talking about targeting data rates of 20 gigabits per second in the downlink and 10 gigabits per second in the uplink. Now, those were the initial specifications. Obviously, we're not going to see those on networks from day one, certainly not with a 3.5 gigahertz spectrum. We'll see those when we introduce the higher frequency bands with much broader channels. But this is really the kind of target. So we think about a similar target in the 4G world. We set ourselves a target of 1 gigabit per second. We standardized 4G back in 2008. we're just at the point now where we're starting to see networks around the world, including the EE network in the UK, actually demonstrating and launching that 1 gigabit per second peak capability. 10 gigabits per second in the uplink is quite a challenge as well. And when we think about uplink, we need to think about different types of user equipment now. It's not all necessarily going to be a mobile phone or even a smart device that's wireless. There could be devices connected into the network that have a wireless last mile, but are actually plugged into the mains and are quite high-power devices. So if you look at the radio specifications, you'll see that we can support the same high-efficiency radio interface in both the downlink and uplink, as well as some fallback options for the uplink as well in the Release 15 specs. So we are looking at kind of fixed applications of this wireless technology as well as mobile applications. Some targets around spectral efficiency here, both of which a significant uplift on what we saw with 4G, 30 bits per second per hertz. We really are kind of pushing the boundaries here, and 15 in the uplink as well. So the 30 is double the spec we had for LTE, and we're more than doubling the uplink requirements here from LTE as well. What's particularly interesting is now we have this requirement for a typical user experience, an indication as to what it should be. Previously, we've always talked about peak rates, but now we're saying, actually, the typical user experience as a target value for enhanced mobile broadband use case should be 100 megabits per second in the downlink and 50 megabits per second in the uplink. Now, we've seen a number of talks today that have shown what we can do with 100 megabits per second. And actually, to deliver 100 megabits per second to a large number of users in a dense urban area means we need to be targeting some of those higher peak rates to lift the average area capacity density up. So as a network architect, whilst the peak rates are something to chase and something that we aspire to, actually the benefit of those peak rates is actually area capacity density for a larger number of users. And then we've got some one-way user plane latency over the radio. So we've got a target of 4 milliseconds for enhanced mobile broadband, and the ITU specified 1 millisecond one-way for ultra-reliable and low-latency communication. However, 3GPP have specified 0.5. So say the ITU specs are a minimum requirement, and in a number of cases, 3GPP will exceed this. 3GPP is already talking about simulations that show data rates higher than these minimum requirements as well, of course. Control plane latency is important. So how long does it take to take a device from an idle state to actually transmitting packets in the network? The base spec asks for 20 milliseconds, although 3GPP is going to meet the stricter requirement of actually targeting 10 milliseconds. Now, that sounds quite generous when we talk about some of the other latency targets, but of course, this is a state transition. It's not a single transmission in one direction, it's a message interchange. So there's going to be a number of messages backwards and forwards, so we need to optimize the number of messages that have to be interchanged for that state change to take place, and obviously the location of the control plane function as well. And then as we move forward to massive machine type communication, 1 million devices per square kilometre. So massive density of devices in the network, and it'd be those kind of density drivers that move us from the NB-IoT type technologies we have today into the requirements for 5G MMTC. And the last one I've picked out, and it's just a sample really, is this minimum requirement for EMBB and URLLC mobility interruption time of 0 milliseconds, which suggests a make before break mobility procedure. Now, we had this in WCDMA, of course, for interfrequency. We had to do a hard handover for intrafrequency. But then we actually moved to a different situation in 4G, of course, where we now do a break and make, and it's typically up to 30 millisecond mobility interruption time on a 4G network. So actually, to do this, it's going to really call upon the separation of control and user plane. And actually, it may well be your control plane is connected on a lower frequency band, and you opportunistically connect the data plane to cells that you see offering capacity. So we think about networks in a different way. We heard from the Huawei presentation before about this kind of cellless concept. So straight into the network architecture. Now, we've seen diagrams like this for quite some time in mobile. Really, from GSM or certainly from GPRS, we started to see this kind of reference point representation of mobile networks. What we've got along the bottom, I think Mishka talked about this earlier as well, is the actual data plane itself. So our user plane along the bottom from the user equipment over the new radio interface into the radio access network itself. And that's actually not as simple as it looks because of that functional decomposition, which we'll explore shortly, out to the user plane function. So effectively, we've collapsed the S&P gateway from LTE PC into a single node. And actually, the practical realization of the EPC in most networks is a single node for S&P gateway, albeit there's some interfaces to manage with S5, etc. And then we go out on the N6. So the SGI, as we know it today, that's where the kind of smarts tend to be, the GI LAN environment, and then out to a data network. Now, that data network could be the public internet. It could be a private intranet. It could, of course, be service platforms on the operator's network. So it could be a CDN, for example, or some other capability. Above that, we have the control plane, the next generation control plane, broken down into subscriber management, authentication functions, and unified data management, as well as a core access and mobility function, a session management function. Now we've got the addition of the network slice selection function, which actually wasn't in the original draft architecture, so things have moved on quite a lot in the last year since I spoke here. Policy control, and then an application function sitting outside of that. Now that application function could well be an IMS, for example, an IP multimedia subsystem to support a voice service. But actually, whilst this is a standard representation, I don't think it's the way we'll view mobile networks going forward. And the next diagram we've definitely seen a couple of times so far is this kind of service-based architecture, where actually what we're saying is that we've got a whole bunch of software capability that we need to put on some kind of common compute platform. Now that common compute platform could be local. I've drawn this here with a kind of a data bus, but of course it could be fully distributed as well. And we may want to put functions in different parts of the network to manage different capabilities. We have the ability to do that. We introduce 2 new nodes to make this work. We've got the NEF, the network exposure function. And that network exposure function allows us to access a shared data layer for data analytics, for example. We've also got a network repository function, the NRF, and that offers a whole range of services, including a kind of discovery function whereby software entities serving these control plane purposes can identify other entities in the compute environment and can connect directly when they need to. So we can be very slick in terms of how we do that communication. I've included 2 slides here, one which explains the terms and one which explains the interfaces as well. So that's just really kind of back up. I just wanted to highlight the fact they're in the pack. So looking at the functional decomposition of the radio access network, we've got our data plane now as it is. We've got the RAN broken down into 2 functional blocks, a distributed unit and a central unit, with a new interface that's been designated F1 connecting between the 2. And the F1 specifications are available in the December release of Release 15. So what does that F1 interface look like? Well, what's been standardized in 3GPP is a higher layer split. So effectively, if we look at the protocol architecture, PDCP, the Packet Data Convergence Protocol, sits in the central unit, whilst RLC, Radio Link Control, along with MAC and PHY, sit down in the distributed unit. And it is worth just spending a few moments to understand these terms, because they are going to be the basis of all the 3GPP specs. And if you've worked on Cloud RAN before, DU often means a digital unit, which is actually the baseband unit, which is now the central unit. So the terminology is important, just to clarify the context of the conversation. We've got additional protocols sitting in the CU as well. We've got the new SDAP protocol, which has been added to manage quality of service and how we manage QoS flows in 5G, which is in addition to the protocol stack we had in 4G. But going for this particular functional split as a higher layer split, it means we don't need to run anything like CIPRI or even eCIPRI over the wide area network. There's still an option to do that. We'll come on to that in a moment. But we can run this on an IP transport network layer over a carrier Ethernet interface. So it looks an awful lot like mobile backhaul as we know it today. And from a dimensioning perspective and a performance perspective, it is very, very much the same. Because we've got non-real-time functions back here in the CU, then we don't have particularly exacting timing requirements on that F1 interface connection. So what will actually determine the latency you allow on the F1 interface will not be the requirements of the radio, rather the requirements of the services that you overlay on top of the infrastructure. I'm showing the F2 interface here, what I'm calling the F2 interface, and I'm suggesting in many cases, certainly in European deployments, I would anticipate that would be an on-site interface, in the same way CIPRI is today in most cases, from a baseband unit in the cabinet on site up to the remote radio heads or active antennas. In this particular case, from the DU on site, which could be externally mounted as well, up to the active antennas, or it could actually be passives. We talk a lot about active antennas and massive MIMO in 5G, and it brings huge benefits, absolutely. But not every deployment will necessarily need active antennas and massive MIMO. And certainly when we get down to 700 megahertz, we're not necessarily going to be deploying massive MIMO arrays in those kind of frequency bands. So we've got a number of options as to how we build that. The F2 interface term is not standardized in 3GPP. It has been used by a number of industry fora, and it has been used by a number of vendors, and it kind of makes sense as a way of describing that interface. We'll see if the term's adopted or not in time. So the practical realization of this network then will be a little different, of course. We're going to have to build that IP or that Ethernet connectivity between the distributed unit on the cell site and the central unit sitting deep in our network. And we'll step through that architecture as to where those central units could sit over the next few slides. In the middle of that, you're going to have some kind of fiber or wireless backhaul. You're going to have a number of layer 2 switches, layer 3 routers, etc. And I've inserted IPsec there. Now, if we're building a simple EMBB network with PDCP sitting on the CU, you don't necessarily need to use ESP. You could use a null cipher. You may choose to use ESP, depending on how you overlay in other services. But of course, the Packet Data Convergence Protocol manages the ciphering, which is going to sit back here, which may well be deep in your network in a trusted and secure environment. It's very likely, though, because it's an Ethernet interface, you're going to want to run authentication. So you're going to want to protect that interface anyway. So therefore, an IPsec functional entity, be that hardware, be it a virtualized appliance, or actually just be it software run on a virtualized compute platform, would provide a level of protection and security there. So in terms of expectations on latency, we've got a number of requirements from industry fora and standards. And we've also got some use cases. Now, I've talked to lots of people about these, including automotive, gaming, health as well. And this is a kind of general consensus that for virtual reality and augmented reality, we're talking between 7 and 12 milliseconds. Yeah. Tactile internet, certainly less than 10 milliseconds. Vehicle to vehicle, yes, less than 10 milliseconds. And I think the point is that mission critical systems on vehicles won't rely on cellular connectivity. I spoke to a chief scientist from a major automotive manufacturer a little while ago, and he said, I do not need 5G to build autonomous vehicles. He said, however, I can make the user experience a lot better if I can have a connected and autonomous vehicle, because I can preempt the need to do emergency braking and brake more gradually before an incident, for example, or I could take other actions to avoid the incident completely. So the term connected and autonomous vehicle, CAV, is very much a dialogue that we should be using when we talk about the future of cars and other vehicles. Then manufacturing and robotics and safety systems could be as low as 1 millisecond, but it could be out as far as 10 milliseconds. So not many things on here are screaming at me saying, Andy, as a network architect, you need 1 millisecond latency on your network everywhere. So let's see what we can deliver on the network and how we can then scale that solution. So a representative network, just to talk you through the concepts of deploying the architecture, and we model this kind of thing, as you can imagine, in considerable detail. So I'm showing an access network there with small cells and macro cells. I'm showing access, aggregation, and core as 3 tiers of the network. So in our case, in BT, the access site is a tier 1 exchange. The aggregation is what we call a metro site, and then the core is one of our regional hub sites. And they connect out to the IP peering point and out to external networks as appropriate. So taking that kind of model and looking at latency figures. Now, this is illustrative. This is based on an analysis of 8,000 sites on our network. We're doing more and more work to increase the number of samples we have here, which may change some of these figures. We've increased it to 16,000 at the moment. But just to give you a feel, about 12,000 sites, about 100 and about 10 at the different tiers of the network. The one-way transport latency, 0.6, 1.2 and 4.2 milliseconds. And again, we're doing various things to optimize that and change that. So this was illustrative in as much as it allowed us to start placing components in the network in the first phase, but it's very much a work in progress. What I've then done is taken those figures that we've calculated for our network and added the 3 GPP figures for the RAN, for EMBB, so 4 milliseconds each way, and for URLLC, 0.5 milliseconds each way, to say, actually, if I want to serve about 10 milliseconds as a round time trip for enhanced mobile broadband, then I could do that in an aggregation site. That assumes, of course, that the content you're serving is in that aggregation site. If you're going to the internet for that content, then you may as well put your core network back here. So you really do need to have the content distributed, and we'll explore that in a moment with a look at multi-access edge compute capability. If I want to serve a low latency use case, then actually this is looking pretty good. Because in my mind, low latency is sub 5 milliseconds, seems a reasonable figure. Ultra low latency could be sub 1 millisecond or 2 milliseconds. We don't really have agreed industry definitions. But effectively, we can serve network-based low latency services, and that fundamentally changes the economics for everybody by having common infrastructure in the network and not having to deploy compute into every single end device. It fundamentally changes the way we build networks. Of course, it puts some pressure on the network from a reliability perspective, but we're building lots more reliability into networks, both through the standards and through the way we're architecting our network now to support the emergency services network. So let's start to overlay some platforms onto that sample conceptual network that we were going to build. Access aggregation core, the functions in red are 5G specific. The IP set kind of comes with it, but it's not 5G specific, so I've not highlighted it in red there. The user unified data management, sitting in there to an evolution of the HSS, that's subscriber management services, that'll sit fairly deep in your network. The control plane function could sit back there initially as well. The user plane function for enhanced mobile broadband will probably sit there, because in many cases the subscriber is going to want to go out to the internet anyway, to the IP peering point, so we could sit deep in the network for that first use case. However, we're increasingly serving content from on-net caches, and over 50% of the fixed broadband content we serve on the BT fixed network comes from on-net caches, comes from that CDN capability. So we're working with a lot of major content partners to bring content on net. You can see the 21C, the heart of our network, our PE routers and P routers running through the core of that. Synchronization at the bottom. So this is the addition of PRTCs, so primary reference timing clocks, effectively to deliver phase synchronization, not just frequency, because we're talking very much about TDD radio interface. So the need for phase sync in there, and you've got the IPsec at the top. So this would give you an enhanced mobile broadband network capability. But let's build that out. We could, of course, push user plane functions and MEC out to the aggregation. So MEC is multi-access edge compute, was previously mobile edge compute, but in IET a little while ago we changed the term to multi-access, so it's available for fixed and mobile. It's an important part of our convergence story. Mishka mentioned earlier some of the FMC work we're doing with Kings and other partners as well. So by doing this now with MEC here, we could have content, we could have compute as a service, we could be hosting NetApps, for example. And having the UPF there means we've got direct connectivity into that multi-access edge compute. That could be built on common NFVI, so common compute platforms as software instances. Of course, we could then push that further forward in the network to offer even lower latency, to handle greater scalability. Certainly if we listen to the kind of numbers that we heard this morning about the number of small cells that could be required in networks, then we may want to distribute more and more functionality. By putting IPsec at the edge, you remove the IPsec overheads from the core of the network, of course. By serving from the edge, you remove some of the core transmission costs as well. So there are a whole bunch of less obvious benefits to distributing more capability in your network. So we've now got a more distributed network. So I could comfortably do a few milliseconds round time trip from this point, which would meet many, many low latency requirements. And I could do that from a network that is robust, that is resilient, and is highly available. But what if you do want to do 1 millisecond or thereabouts? Well, actually, we could look at distribution even further in the network. We could distribute control plane functions as necessary, we can access locally, or we push right the way out to the very edge of the network. So here I'm showing a 5G DU with its CU components, its user plane function, and its multi-access edge compute, all on the cell site. These distributed units themselves are effectively compute platforms running software, so actually we can put more and more capability onto those platforms. Now, that could be a standard macro cell, or alternatively, it could be a bespoke solution that we build in a factory, in a hospital, in a manufacturing plant, for example. So there's lots of ways we can actually customize that as a special projects application to meet specific demand. And we're engaging with a wide range of verticals at the moment to understand those opportunities and how we bring propositions to market. We talked about small cells very briefly. Certainly, Ms. Curie's presentation earlier mentioned the need for huge numbers of small cells to really lift area capacity density. We agree that small cells are an integral part of 5G. We're doing a couple of small cell trials at the moment that are 4G focused, but 5G will be a big. 5G will put an even bigger drive and demand on that small cell program. So, in terms of connecting these things in, we're looking at a base connectivity solution, which is fiber based. I'm showing an example here of a fiber ring and a couple of fiber spurs. The dashed line there is suggesting some kind of wireless backhaul as well. We're particularly interested in what's happening in the higher millimeter wave bands as well, particularly the work in ETSI ISG on millimeter wave transmission, looking at D band, so 140 to 170 gigahertz, some very, very high capacity short range links there. We've simulated 50 gigabits per second over a few hundred meters. So that could be plenty for the kind of thing we're trying to achieve. In terms of wireless and fiber distribution for the next phase, well, we're going to have a hybrid of that. Fiber where we have it, wireless where we need to effectively. But then what happens when we really do go for ultra dense networks with 26 gigahertz? Well, 26 gigahertz, we've heard a number of references today to self backhauling. I am a believer in that. I think it's going to be a very efficient way of dropping a site in. There's a few ways it could happen. There's 3.25 gigahertz of spectrum in that 26 gig band, as we call it. So operators may have enough spectrum to allocate some for backhaul, some for radio access. Or actually, with the spatial multiplexing benefits of massive MIMO, potentially there's a reuse probability as well for radio access, possibly not over the whole 360 degrees of that cell or whatever angle it's covering, depending upon the antenna array. But potentially in some areas, whilst directing backhaul in another area as well. The backhaul will be line of sight. You can probably use a higher order modulation scheme with less coding than you would do for the radio access environment as well. So there's a number of things to consider, and effectively that means we then deliver a very, very dense network with simple connectivity. Now, of course, what that does mean is anything you're doing on wireless or fiber-based backhaul will have to scale to support that massive area capacity density. So whilst today I'm busy rolling out 10 gigabit per second circuits for backhaul into the evolved 4G network, in the future, whilst 10 gig may be sufficient for a 5G macro with the option 2 split that we saw before, PDCP RLC, between the CU and DU, these small cells are going to need probably 25 gig backhaul, which means the fiber connection points are probably going to need 100 gig. So 100 gig, which is currently a core network technology, needs to very quickly become a metro and then an access technology. Of course, the volumetrics with that will drive down price, but we desperately need to see innovation in that kind of fixed environment as well to bring the fiber costs down. And I know there's lots of work going on in a number of universities, and I think we might hear a little bit more about that this afternoon as well. So in terms of what we've been doing, just to start to sum up, we've run a number of trials. We're working with many partners. We're working with Huawei, we're working with Nokia, we're working with Ericsson, we're working with a wide number of universities from Surrey to King's to Cambridge to Bristol to the University of Salford, where we're doing work on microwave and millimeter wave transmission. And what I'd like to do is just show a video in a moment that shows the actual 2.8 gig end-to-end activity we finished shortly. We've also been doing some massive MIMO testing at our labs at Astral Park. Our research teams are really starting to understand the detail of spatial multiplexing and massive MIMO and what that means for us. And also, we recently did a demonstration of kind of uplink and downlink decoupling to show how we can support the wider coverage from the 3.5 gig downlink on the uplink as well. So some interesting developments in that space. So I'll just fire this video up for a moment. It's only about 1 minute 40 seconds, but it gives you a feel for some of the experimentation and development activities happening in our company.
Hi, my name's Tom Bennett. I'm the Director for Technology Services here at EE. What we're delighted to demonstrate here today is an end-to-end 5G network. 5G new radio with massive MIMO on the antenna array, a 5G packet core which is virtualized, all in partnership with Huawei here at EE's labs. One of the great things with this end-to-end demonstration is that we're using commercial off-the-shelf hardware in our packet core. So it's Huawei software on HP hardware. We're consistently showing 2.8 gigabits per second end-to-end through our RAM and core. For us, that's a great step forward in utilising and showcasing the promise of 5G.
Okay, so in that particular demonstration, we used 100 megahertz of spectrum. We used a 7:1 downlink to uplink ratio on that TDD configuration, 64T, 64R for the base station, and the actual UE was 48R. That's configuration sitting behind what you've just seen there. So to summarise, 5G will address a broad number of use cases, from enhanced mobile broadband to ultra-reliable and low latency communication. And I should also, if I break it out down the bottom here, I always try and make this point. Ultra reliable and low latency is one grouping, but of course some services may require ultra reliability, but not low latency, and others may require low latency, but not reliability. So there's actually 3 subsets of service type that you would need to address from that. And of course we mentioned as well the evolution of massive machine type communication. 5G requires a new architecture, so this is a chance to really embrace the world of network functions virtualization, the world of softwareization through software-defined networks and flexible network architectures. I agree with Miska, 5G has to be the last G because a number of reasons. One, commercially it's not viable to keep doing forklift truck upgrades every 10 years on networks. Of course we'll continue to evolve the technology, but this should deliver everything we need to get people to the point where actually upgrading to the next G gives them nothing more. You know, we'll continue to manage that service and manage that experience. So 5G is fundamental in shaping the future. We talked about next generation core network and how it can be grouped into a control plane function and a user plane function. Some RAN functions are going to be pulled in towards the core, while some core functions are pulled out towards a RAN. Now, that introduces a new kind of node towards the edge of your network, and that new node will not be in a fixed location, hence the need for softwareization and NFVI. We'll need to push that capability right to the edge of the network in some places and have it in different locations for other services. So that next generation control plane, based on service-based architecture, will allow a device to connect to both a locally hosted service and a more centralized hosted service. So it may well be an enhanced mobile broadband internet browsing session along with some kind of critical communication activity running in parallel. Small cells are an essential component of 5G. URLLC is an overlay on the existing infrastructure, so we build the network and then we pop that on top of it. And the last point there, the initial machine type communication use cases will be addressed by narrowband IoT, and that's being rolled out now. Great advantage of narrowband IoT is you get about a 20 dB improvement on the link budget because of the radio characteristics, so it gives you much better geographical coverage as well as in built-in penetration. So, thank you very much.
Do you have any questions for Andy, please? Any questions? Over to you, please.
When we talk about 1 millisecond.
Yeah.
Sorry.
Hi.
This is Reza Khavan from Future Cities Catapult.
Hello.
When we're talking about 1 millisecond delay or latency, is it device-to-device communication in connected car? I mean, we are not using the network itself.
Yep.
Am I right?
The network has been designed to support 1 millisecond or thereabouts with a 0.5 millisecond specification on the URLLC. It could be, but those two users will be served from a very local base station and very local content. You're not going to be going back out to the internet and back out again. So you can build local networks that can be network assist. So V2X, for example, could work with very local capability, and that capability could be compute capability, for example. Or it could also be device to device. And device to device, I've not touched on today, but that will be a vital part as well of what we build in 5G. Building on the work on proximity services, etc., in 4G today. Yeah.
Thank you.
We have time for just one more question.
James Say from Roke Manor.
Hi, James.
That's a very good presentation, thank you.
Thank you.
It all sounds very expensive. So are there any thoughts on how the business models might need to change to support 5G investment?
Yep. The key thing is we need to be focusing on new use cases. So we need to be engaging with the verticals and kind of generating revenue sources from kind of non-traditional routes, I guess, for cellular. I think from the conversations we've had today, I've talked to a few people in the room, and the presentations we've seen so far, those verticals are there actually. So I don't think it's so much the operators trying to push the technology. I think there is a level of pull. So we need to find the opportunity to monetize those verticals. But absolutely, it is a significant investment we're making. 64T, 64R antennas are incredibly expensive. But actually, they're not necessarily needed everywhere. There will be evolutions in the technology that brings the cost down. And there will be more variance between an 8T, 8R and a 64T, 64R solution. But also, the addition of millimeter wave as well means we can actually deliver very high capacity in small form factors. So the types of site we build to lift area capacity density could change as well. So there's a number of things we're addressing really from both an infrastructure perspective in terms of trying to drive cost down and deliver capacity in a more efficient way. And certainly in a cost per bit analysis, 5G will be a lot cheaper than 4G, as 4G is a lot cheaper than 3G. But actually we do need to monetize the new services as well, absolutely. Yeah. Thank you.
Thank you very much. I'm sure Andy will be happy to ask questions.
I'm around all day, yes. I think I need to dash off now for a quick interview on IET TV, but after that I'm around, yes.
This concludes this morning's session. Lunch is served downstairs. Please convene back at 2 p.m. Thank you.
Thank you.